In a previous lecture video, I introduced the concept of frequency histogram and showed you how you can look at the frequency histogram and get some indication of the lateral spread or the lack of precision relative to some central or mean value. So what we're going to talk about now is a way of quantifying that using something we call the standard deviation. So deviation essentially means the difference between a measured value and the mean. And standard just means essentially that's like a typical deviation value that characterizes those measured values. So that's what we're going to do in the next couple minutes. So and this is the slide that I was referring to. Here we have two frequency histograms. This one has a much greater lateral spread than does this one. So we'd expect it to have, in this case, a higher standard deviation down here. Let me get the right pen here. A higher standard deviation down here in this slide, in this frequency histogram, and a lower standard deviation up here because the spread, in other words, the lateral spread about the mean value is going to be less. So let's see how we do that. So in this case, what I've shown here is a bar chart for each of 20 samples. Okay, and so again, I'm using this same physical property we talked about before, this gap width, say for automobile manufacturers. And you might imagine that you might take that gap, all these gap widths, and find the mean value. And let's say the mean value is right here. In fact, it is for these 20 values is about 0.9, slightly greater than 0.9. So you see some of the values are greater than 0.9, like number 1, number 3, number 4, number 5. Number 12 especially is greater than the mean value. And number values are less than that mean value, like number 2, sample number 2, number 6, 7, and 8. All right. So each one of those deviations, essentially how far you are from the mean, can be written as epsilon sub I equals y. This actually should have a I subscript on it, minus y bar, y over strike. And this is the mean value of y. So this one is the mean value. And the y value is essentially a single measurement. This is really coming out bad. Sorry. Mean value. Sorry, I did that with my mouse. So that's the y bar. That's our mean value. So for example, epsilon sub 12 means we're going to look for the deviation for sample 12. So I'm going to come here to number 12 right here. And you can see I'm subtracting off the value, which is 1.43 minus 0.92. So we end up with a positive departure or deviation of 0.51 millimeters. All right, so one thing you might think of, well, why don't I just take the average of all my deviations? Wouldn't that give me a representation of the typical deviation? And the problem is if you have a symmetric distribution like this one, if you take the average deviation, essentially because you have some positive and some negative, you're going to end up with something approaching 0. Even for a large spread or a small spread, you're still going to end up with an average deviation of about 0. So it's not a good indicator of a typical value of, I should say, a typical deviation value. Okay, it's not a good indication to just take the average of those deviations. So what you might do, and what is typically done, is we're going to take an average of the square of those deviations. So epsilon I, remember, is my departure at one single measurement. We're going to square those values, sum up all the values. Sum is like we did before when we took a mean. We just add up all the values, and then we divide it by not n, but n minus 1 for reasons that are probably just too much to deal with right now. And then we're going to take square root of that. and that's going to give us our standard deviation. So as I wrote here, it's the square root of the average, and I put average in quotes because we're using n minus 1, of the squared deviation. So you take the average of the squared deviation, and then you take the square root of that, and that's our standard deviation. The units of standard deviation are essentially the same as the actual measured value. So in this case, if we have a measured gap and we take the standard deviation of that measured gap, the units on standard deviation are also going to be in millimeters. All right, so here's an example of calculation of standard deviation. So we have 10 measurements. Here are the measured values. And then down here, we get the mean of the measured values. Now in the third column, these are going to be my deviations from the mean. So I have 2.27 for my first sample. I subtract off 1.12 and I end up with 1.15. That's my deviation. In the next column over, I'm going to square that value. So 1.15 squared essentially is going to be equal to 1.32. We're going to do that for each of our 10 samples. And then I'm going to, well, in this case, you can see if you take the sum of the deviations, you end up with 0, which is what I was telling you before, why that might not be a good measure of the typical standard deviation. So I'm going to take the sum of the square deviation, that's 4.43, and I'm going to put that into my equation here. So we end up with 4.43. Then we have 10 samples, so I'm going to divide that by 10 minus 1, take the square root, and end up with 0.70 millimeters. So that's my standard deviation of these 10 measured values. So that hopefully will give you some idea of how you do these calculations. And this is just showing you 2 examples. Here's one where I've calculated standard deviation of 0.25. Here I have a standard deviation of 1. So obviously the higher standard deviation is associated with more of the spread. And what you find is that, that's all I said here, we frequently use sigma, the Greek letter sigma, as the standard abbreviation for the standard deviation, or the abbreviation for standard deviation. If you have a bell curve, the standard deviation or normal distribution, that tells you something about the percentage of values that fall within some range about the mean. So for example, if this is our mean in the middle, if we go up 1 standard deviation and down 1 standard deviation, remember the standard deviation is in the same units as your measured value, it's going to encompass essentially 68% of all of your measured values. If you go out 2 standard deviations, that's going to essentially include 95% of all the values. In other words, 2 standard deviations up and then 2 standard deviations down. And finally, you should be aware, while we've been talking about standard deviation, there is another term called variance, and it's frequently represented using a sigma squared, and it's essentially just the square of the standard deviation. So here's just the formulaic representation of that.